the start of this unit, the statement I made was, this is a different way of thinking about things. There are choices you're going to have to make and decisions you're going to have to make, but if you follow a procedure, it can help lead you to an answer. That in every single one of these, you should be starting from scratch and beginning by just asking yourself a set of straightforward questions. I've tried to provide you with those questions. Some of you are continually trying to look back at the last example and make this one conform to the last example. That is not going to serve you. I can always come up with an example that doesn't conform to anything you've seen before, and so can the AP graders. This is not like your other classes. It's just not. You'll have to think independently and think for yourself, and treat every case as fresh. Can we agree the box accelerated? That makes it a first or a second law problem. It's got to be a second law problem. It has to be. So, this problem begins the moment the box is on the ground. That's when I said start the stopwatches. Is there a fundamental force acting on the box? What direction should I draw that force? Is the force in contact with a surface? What's the name of that surface? The floor. So when I draw my normal force, how should I draw that arrow? All right, so we're looking at an arrow drawn straight up. And are we in some amount of agreement about the size of this arrow? Meaning, did you notice that the box was accelerating up or down? Did it accelerate up or down? I mean, did it sink into the floor? Did it somehow fly off of it upwards? Did either of those things happen when you watch the box? So I should see a picture of balance up and down. Was there any other surface connected to the box? Okay, was there any cable, rope, or string connected to the box? Was the box sliding across any surface? Okay, so now we're dealing with friction. So friction has to be along the surface, so it's left or it's right. Now that's a decision, but I've kind of made my box look like it traveled to the right. So I think I'm going to draw my frictional force to the left. These are the forces that act in my system. That's it, these three forces. Now, from here, we have to decide on a coordinate system. But if you couldn't get these three forces, and there's about 12 people who couldn't. So out of 28, that's substantial. Some of you have extra forces. Some of you have the weight broken up into components. I don't know why. I know that I can't think of anything that conforms outside of this list of 5 things. I was not pushing on the box after I left my hand. So for those of you who have a pushing force, it's true that when I threw the box, that was a set of unbalanced forces of which I had no idea about because that's not part of this problem. The problem begins with the box already in motion. A force is not required to keep the box in motion. But the box's motion didn't get maintained. It slowed down. This looks unbalanced to me. Does it look unbalanced to you? That fits what happened. The box slowed down. You're required to place a coordinate system on here to solve the problem. You may choose any direction for X that you wish, but I gave you 2 priorities. 2 things to make this go a little bit easier on you. And one of them was, and it was your first priority, to try and align the x-axis with the direction of the acceleration. I hope that it's not a huge stretch that the acceleration was horizontal. So I'm trying to line up the x-axis with the floor, which means the y-axis up and down. Now you do have to, at this moment, decide on positive and negative, and the box was moving this way, but was slowing down. I'm going to go ahead and make the negative direction the direction of friction. Why? Because I'm pretty sure my acceleration's negative. I'm sure when I plug the numbers in, it's going to give me a negative number. It slowed down. And although that's not definitive, I could say the box was moving in the negative direction and therefore the friction was positive. All of these words coming out is me just babbling because people are still trying to figure out why there's only 3 arrows here. But I want you to understand these are the only things acting on the box. This decision I'm making right now doesn't really matter as long as I'm consistent. Positive, negative, pick a direction. Same for up and down. Pick a direction. None of these things that I'm saying about this are things you have to decide on, really. You just put a positive side on one side and a negative on the other and go with it. Now, apply Newton's law. Requires first that I take this and break it up into net force in the x direction, net force in the y direction. You do have to make a decision here. One of these gets MA, one of these gets 0. Which side looks balanced? It gets 0. Which side looks unbalanced? It gets MA. Now, again, I'm going to stop here, and I'm not trying to make anybody feel bad or guilty or feel like they're outmatched. You're overthinking, in many cases, what has to be done. And you don't have confidence in your choices, which makes it worse. But remember, you don't have to make many decisions. There are rules for each thing here. You have to know the rules. That's what you're doing. You're skipping around. Don't. Do I ever skip around in these problems? Have you noticed I do every single thing exactly the same way every single time, starting at the very top of a list of things? Are you opening up your notes to that list of things when you start this question and starting at the top? Or are you just turning back to the last one we did? I guarantee you, if you do that, I will come up with something in a minute that you've never seen before, and you're going to flip out yet again because you're not going to get it right, and you're going to wonder, I don't have any idea what I'm doing. Start at the top. Work your way down. Apply these rules. They really don't leave you much wiggle room. At least I don't think they do. Add up, and I say this, but add up all the forces in the x direction and take into account their direction. I should put the little bar here to remind you they are vectors. There's only one in the x direction. Add up all the forces in the y direction, take into account their direction. I'm writing it like this because yesterday somebody asked, why are you subtracting them? Okay, I'm not. I'm adding them. It's a summation. But some of them are negative. And I'm just cutting out that middleman. But it is plus negative weight, truthfully. It will have the same effect of saying this. Now, that's it. That's all Newton's laws can do. They didn't solve the problem. They never do solve the problem. They produce a relationship that you might be able to use to solve a problem. But they do not solve the problem. So we use Newton's laws to get to this moment and then decide if there's something we can do with this information. You might have stopped here, but trust me, if you could stop here, I'd be pretty happy that you got here after what I saw when I walked around the room. Because now you are asked to find the coefficient of friction, which means, is there something here that you could use to figure out the coefficient of friction? You have to have context. You have to know where the coefficient of friction shows up. And we already have this context. We know that friction is equal to mu times the normal force. So if I want to figure out mu, I need the frictional force and the normal force. Looks like I have a means to get there, but I don't have the answer. I have minus MA equals mu mg. Substitution, right? So solve for mu. Mr. Shelton, are you going to give us the mass of the box? No. Still not the answer. Right? Still not. But I think I have a pretty positive bead on what it's going to take to get the answer. I need what the box's acceleration was. I know g, but I need the box's acceleration. Are there any context clues as to what I can use to get the box's acceleration? Well, look, it traveled 5 meters in 1.7 seconds with a final velocity of 0. Sound familiar? Remember when I said, got to do the kinematic stuff because it shows up later? It shows up later. Here's later. Is it physics? No. Is this physics? Yes. You might be disappointed now that you know what physics is. Now you can find the acceleration, plug it in here. Do I need to do the rest of this problem? Because I think the hard parts have been covered. But this, it's hard for me to articulate that this is not the way of thinking that you are used to. And although you might not feel this way, I'm doing everything in my power to make this as easy as possible. It's a procedure. Follow the procedure. It might not lead you to an answer, but it will lead you to something that you should be able to use to get your answer. Alexander, do you have a question?
Yeah, I found the mass, and that's how I did it, and I have the same answer. So
Can't find the mass.
okay. No, well, I got the same answer. I got the same exact thing.
Well, sure, because no matter what you found for the mass, it canceled out.
Sure, yeah.
I could have told you the box was 20 kilograms. I have no idea what the mass of the box is. I never weighed it. First period, I told them the box was 2 kilograms because it was first period. They were AP1. They wouldn't do it this way yet. But for you guys, yeah, if I don't think you need it, I'm not going to give it to you. I would only give it to you to distract you at this point. I want to talk about something else today. I'm a little nervous about this because this is tough. And if I'm going to give you a quiz tomorrow, it could be this. So I'm going to do things a little different in this class than I did in third period. So let me introduce you to a question. And let's see if, trying to think, no. I want to talk today about static friction. Static friction brings up something that is different, maybe perhaps more difficult, but maybe perhaps just different. So in order to discuss static friction, I want to remind you that static friction is sometimes called starting friction. And it represents the amount of friction you must overcome in order to get something to start sliding. And I believe when I was talking about this last, which might have been yesterday or the day before, I had you guys put your hands on the front of your desk and to press on your desk. And I would encourage you to do that again. Just drop your pencils for a moment, put your hands on the front of the desk, place your hand on the desk, and recognize that as long as the desk isn't moving, and I'm not challenging to try to get your desk to move, I'm trying to remind you that as long as your desk isn't moving, that there is a frictional force against the legs of your desk and the ground. Now, you, and some of you are a little competitive out there, I can already see it, could apply more force to the desk. And you'll notice that even with more force, the desk might still stay there. It isn't because the frictional force is the same all the time. It's not. The frictional force changed. You could push even harder, and I am confident eventually the 4 or 3 of you will probably get the table to move. I hope. With 3 people pushing, it should still work. And Chloe finally got the table to move on her own. But she had to stand up because the first thing that happened when she pushed on the table, she went backwards. She broke the frictional force between her chair and the floor before she could break the frictional force between the table. Now, I'm not bringing this up arbitrarily. How do you express that mathematically, that the frictional force can be any number up to a point? And the mathematical way of expressing that is an inequality. We're going to use an S to indicate static friction. This means that friction can start at 0 and increase until it reaches a maximum. Problems with an inequality have threshold values. And I use this word a lot. A threshold is a boundary. At a boundary, things happen. Things are unpredictable generally at threshold values. We don't want to push our system to a threshold value because then things will behave in a manner that might be inconsistent. But it's hard to understand how to deal with inequalities because you can't use standard rules of substitution when you have an inequality. Not if you wish to preserve the inequality. Now, if you've never heard that phrase before, preserve the inequality, it's going to come up a lot this year. I use it all the time. It's how we deal with threshold. We want to be left with an expression at the end that might have an inequality in it to understand whether we have to be greater than something or less than something. So we're going to talk about how to preserve an inequality in the context of a couple of examples in here. And so here's the first. So in finding our threshold value, we've got the book, we've got the cover of the book, and we've got the probe. So your job is to draw a free body diagram that highlights the forces that act on the calculator. Again, you don't really have many choices here. So this one is one where we've done this before, and your diagram is going to look exactly the same as the last, I don't know, half a dozen times you've drawn an inclined plane diagram. So at this point, I'm using this example because my hope is you won't make a mistake here. But because I believe in consistency, I will do this problem exactly the same as I've done every other one. I'm going to start by drawing a dot to represent the force, to represent the mass of the object. I'm going to draw a downwards arrow because I believe that the object is experiencing the force of gravity. I'm going to recognize that the object is in contact with a surface. Therefore, there is a pushing normal force that acts on the object, and that force must act perpendicular to the surface. So I think that looks perpendicular to me, so there we go, perpendicular to the surface. I take great care in drawing these as carefully as I can. I look at your pictures and I decide how much you're invested in knowing this by the care in which you draw your pictures. Not because I'm trying to rate you, but if they don't look like they're supposed to look, that often can throw you off. So I'm taking great pains to be as careful as possible here. I believe there's a frictional force that acts to keep the calculator from sliding down the ramp. That frictional force has to be along the direction of the ramp. So I'm trying to make sure it looks just like the ramp. That looks like it, and I'm going to draw it right over there. Why is it smaller than the normal force? Because friction is always smaller than the normal force. Yes, I'm trying to make sure it's balanced left to right. That's true too. But it's always smaller than the normal force. Those are the only forces that act in my system. There's no cables or pulleys on there. So now, well, I'm thinking a coordinate system. And yeah, we've done this one before, so I'm going to use a coordinate system that is aligned with the ramp. Why? Because it's lined up with more forces than if it's lined up with the weight. But that does leave one force that has to be resolved into components. And let me just tell you something here, folks. When you're considering their two components, one of them has to be this direction and one of them has to be that direction. That's really what's happening here. We draw it as a triangle, sure, because as triangles go, that's where sine and cosine factor in. But ultimately, the forces actually act at the center here. So I'm going to continue to draw it as a triangle because that helps me with the sine and cosine. It tells me that this side is related to sine and that this side is related to cosine. So I get mg sine theta and I get mg cosine theta. Yeah, I substituted mg in for the weight. I think I can do that. Now, this isn't our first time doing this, but I'm going to do something here just to switch things up a bit. When I draw in the components, what I'm actually doing is replacing one vector with two. This is what's actually happening. And now I'm doing this for people who can't visualize this well, but I should have two vectors in the x direction that show balance, so it doesn't accelerate in the x direction. And I should have two vectors in the y direction that show balance, so it doesn't go anywhere in the y direction. And although there might be more forces, I at least have these. So now net force in the x direction equals 0, and net force in the y direction equals 0. This tells me that mg sine theta must equal friction. Jumping ahead a little bit. But all I would have written is mg sine theta minus f equals 0. For the same reason that n must equal mg cosine theta. Again, yes, jumping ahead. N minus mg cosine theta equals 0. Now, when I reach this point, I have reached the end of what Newton's laws can do. This is it. Every time we get to this point, I always stop and say, this is what the procedure does. This doesn't solve your problem. But at the end, you will get two relationships that may or may not solve your problem. Doesn't matter whether they do or not. This is what Newton's laws do. They produce these relationships. And it always produces two per object because all of our problems are two-dimensional. If we had three-dimensional problems, it'd produce three per object. Now you were asked to come up with a relationship between theta and the coefficient of friction. There's no coefficient of friction in either of these. It's at this moment that you decide whether you can use these or not. And that's when I look up here and see, well, I see coefficient of friction. Do you see that? So I'm going to do some substitution. And now I'm kind of out of room, so come on, be my friend. Nothing? There we go. Now, here's where I will caution you. If you wish to preserve an inequality, here's what I'm actually asking you to do. You must start with the inequality. And you substitute into the inequality, not out of the inequality. This is how you preserve the inequality. So instead of plugging this in for F, you don't do that. We take everything and plug it into the inequality. This allows us to know what direction the inequality stays. So when you have to preserve an inequality, you substitute into the inequality. The inequality is like the skeleton equation and everything goes into it. So if you don't know what I mean by that, because I'm looking at some confused faces, friction is mg sine theta. Less than equal to mu s times the normal. The normal, mg cosine theta. I have preserved the inequality now, meaning I know what has to be less than what. Now, since I'm trying to find a relationship between mu and the angle, I should get the angle on the same side. So I'm going to first notice that part. It goes away. All right, mg's on both sides, get rid of it. And then I'm going to divide both sides by the cosine of theta. This leaves me with sine theta over cosine theta is less than or equal to the coefficient of friction. Sine over cosine is tangent, right? So that shouldn't be lost on you. That means tangent theta is less than or equal to mu. Now, why? Why, Mr. Shelton? I'll tell you simply why. Why did we do this? Well, we have a relationship now. I have a relationship between the static frictional coefficient and the angle. So why bother? It's simple. I don't want my tires to slide with respect to the ground. Do you? When you drive, your tires don't slide. A point stays in contact with the ground at all times. They don't slide, which means static friction acts on your tires all the time. If I'm building roadways, I want to make sure that I don't build them so steep that the tires will break static friction and slide. I now know exactly the threshold that I have to stay beneath. Notice, tan theta has to be less than mu. If it's greater than mu, bad things happen. If it's less, I am okay. Do I even want to approach equals? Probably not. Not if we're talking about a road surface and your tires. So this is like the rubber and the road surface. This is the angle of the overpass over by the airport. Right? You've driven near there. You've seen all those banked angles. When the car makes that turn, the angle has to be chosen so that the car doesn't slide down the slope and off the overpass. And it's not an arbitrary value. But this is always changing, right? Here in Florida, it rains. If it rains a little bit, that thing drops very low. Why? Because the oils come up. If it rains a lot, it actually gets better after a time because once the oils get washed away, the roads get a little stickier. So we probably don't want the coefficient for tires and road surface, but the least coefficient that exists. We do this because this is what engineering is about. This is why there's physics. It's predictive. This is how you solve a problem. They did not just arbitrarily choose some angle because they thought it would be fun. They chose that angle to ensure the safest possible commitment to all cars on the roadway. Do you notice that the mass of the cars isn't in this at all? You should notice that, which means it can build one angle that works for both trucks and small cars. The mass canceled out. That's convenient for us as drivers. Could you imagine if it wasn't like that, where you'd have to select your lane based on the car's mass? That would probably make driving harder for you, since most of you don't know what the mass of your car is. So I'd argue that the point of having this ability, and the reason why you're not going to see a lot of numbers here, is because it does produce for you something that is now useful, that you can apply to multiple circumstances. And threshold problems, well, that's life. This is how life works. So when you grab that wrench and it says don't over tighten, that's what they're saying. There's a threshold. If you tighten too much, you will break that threshold and you will be sad.